included in your recording, so we wait for the
Yes.
technician to.
Okay. Shall I do it over again with the?
Yeah. So,
Yes? Let's do it now?
Yeah, sure, sure. You
Yes.
can stay there, yeah.
De kandidaat.
Dank u, Madam Biel. Ik open de zitting van de commissie ter beoordeling van het proefschrift en de stellingen van Mohsen Boudas, Master in Civil Engineering, University of Tehran, Iran. De verdediging zal in het Engels worden. A warm welcome to you all at this public defense by the candidate of the dissertation entitled Discrete Fiber Models Beyond Classical Application. The Board for Doctorates of Delft University of Technology has installed a committee to evaluate the thesis and proposition. The committee will have a debate here in public with the candidate, and it's an honor to present to you the members of the committee, to whom I extend a hearty welcome. On screen, first of all, we have Professor Asp, Chalmers University of Technology, Sweden. Thank you very much for attending. Then we have as second opponent, Professor Böhm, Technical University of Vienna in Austria. Third, we have Dr. Gijselaar, University of Twente. And fourth, Dr. Aragon, Delft University of Technology, Faculty 3M East. Number 5, Professor Schlangen, Delft University of Technology, Faculty of Civil Engineering and Geoscience. And number 6, the co-promoter, Professor Simone, also Delft University of Technology, Faculty of Civil Engineering and Geoscience. And then present in this room, the promoter, Professor Sluis, Delft University of Technology, Faculty of Civil Engineering and Geoscience. Thank you all for taking part in this academic ceremony. My name is Arthur Meinet. I'm Emeritus Professor of Water Science and Engineering at Delft University of Technology and IHE Delft. It's my pleasure to chair this session on behalf of the Rector Magnificus of Delft University of Technology. I would now like to start the opposition and give the floor to Professor Asp.
So, Barbara Mendes, I have a few questions I would like to ask you on your thesis, and I will focus my questions on the chapter number 5, which is on structural batteries, four structural batteries. And as a first question, I'd like to ask you on page 108, you state the objective of the paper to be development of embedded methods similar to those for mechanical systems for electrochemical systems. This is all good and considered, in my opinion, a fine contribution to the field. However, you also discuss on the same page the fibers, electrodes, and separators that they bring mechanical multifunction capabilities to the material, which can be labeled as structural battery. But you have not studied the multifunctional performance of the material, solving the fully coupled mechanical electrochemical problem. Why did you not combine the mechanical and electrochemical models?
Hopefully the opponent, thank you for your comment. Well, we had multiple objectives in this thesis because the embedded reinforcement methods from a mechanical purely mechanical point of view, they were not very well understood. So we invested like 3 chapters just to understand the mechanical aspects. So in chapter 5, which we discussed fiber-based batteries, basically, we tried to keep it simple because we wanted to basically discuss the electrochemical process, because there are many, it's a very nonlinear process at the interfaces. It's a highly nonlinear interfacial rule, and it had so many parameters, so we wanted to really, at this stage, to keep it as simple as possible, so that we can really, in very details, we can't really discuss all the effects of the diameter, different parameters. In my opinion, to combine it with the mechanical part, it's not a major computational step. You basically, from a numerical aspect, it's just combining the two numerical tools. So that was one reason. Another reason is that because we try to keep it general in the sense that we wanted to also address other electrolyte materials in which they are not essentially solid. So this will give this work a more audience probably, and without limiting it to a solid electrolyte material. So it was, I think it was an initial step in this, so that we can, in the future, there is definitely a lot of contribution can be done. Just, I mean, from a numerical aspect, I don't think there is much to really do compared to what has been done. It's just a combination of two numerical tools, which are very similar in many aspects. But there is definitely a lot of physical considerations which should be done and which should be taken into account for the future.
Yeah. So you mentioned nonlinear electrochemistry. Do you expect you will need nonlinear material mechanics as well? So you mentioned that you expect nonlinearities in the electrochemical analysis. Do you expect nonlinearities also in the mechanical analysis?
Definitely. I mean, if we want to study fracture, for instance, there are definitely constitutive relations which are really not. The elastic one for sure is not working. So we have to really consider very advanced constitutive relations, and also maybe to model fracture or damage is definitely gonna be very challenging in that aspect as well.
So I want to build on this for my next question. So on page 119, you state that you represent the active material types as one-dimensional objects. And in the paragraph below there, you actually state that the extent of field variable gradients on an arbitrary cross-section perpendicular to the fiber are negligible compared to the extent of field variable gradients along the fiber. This is, I think, true for many of the properties, like for instance the diffusion concentrations and so concentration gradients and so in the fiber. But for the expansion, the swelling and the shrinkage of the electrode fiber during lithiation electrochemical cycling, it's actually the other way around. We have seen that the radial expansion is about 10%. And that's the same for graphite also, 10% out of plane, whereas only 1% along the crystal or along the fiber. So that corresponds to a volume change of 21% for the cross section in that case, which is similar to the volume change. What would you say is the consequence of this radial swelling, and how would you be able to catch that with your model, since you assume the one-dimensional object? And when you did this 3D analysis data on in chapter 5.5, did you consider the swelling in the fully 3D case or not? Did you look into this consequence of radial swelling? Do you think it's important?
Yes, thank you for the question. So no, basically the swelling has not been taken into account in our simulation because of the reason which I just mentioned. This was basically the initial step in modeling this type of numerical modeling of this type of fiber-based electrode materials. So we wanted to keep it as simple as possible to really, at this moment, we just wanted to find basically a range of validity for this type of numerical models. As you mentioned, definitely swelling can have an important effect on the electrochemical process for sure. and it should be taken into account for a proper numerical simulation in the future. I can.
Don't you think that if you have a mechanical system with a high volume fraction of fibers, that it also has a major role on the mechanical performance?
Exactly.
As well as by 20%.
Yes, exactly, because it can cause stresses inside the material, and then definitely there can be mechanical load. I mean, yeah, definitely it's very important also from the mechanical point of view. But what I can say is that including the effect of swelling, if you want to really change the geometry in an explicit way, it's really impossible, it's very difficult, using the finite element, for instance. So we need to have a kind of an approach which takes account its effect in an implicit way. So for that one, we have a very, we see a possibility to use the same embedded approach in a way that, well, if you look at the initially from the electrochemical point of view, we can define really the gradients of the concentrations inside the fiber material. If I know there are some studies that have been done for particles in which they link the concentration gradients to the surface fluxes, for instance. So we can assume that there is a predefined shape for the concentration gradient. So in that way, we can really define a non-homogeneous diameter within the fiber. But that has to be studied. But I don't see that a major numerical step. It can be done in a very convenient way with the same framework. From the mechanical perspective, also we can come up with something similar. I mean, like what we have like with the thermal expansion, the way that is coupled to stresses. I mean, we can come up with something similar here as well. So I think in the end, with the same framework, very simplified numerical model, we can still have these effects.
Thank you. My director. I'm done with my questions. Thank you.
All right, thank you very much, Professor Haas. May I invite Professor Bohm to continue the opposition? Maybe Professor Haas could mute his microphone and Bohm activate. Screen will come up. There we go.
Mina Rector, after stating that this is really a very interesting and impressive thesis, I would like to start my questions with a query for details on proposition. I think it is 6.
Okay.
Where candidate states.
One moment, please, Professor Bohm. I will ask the candidate to read out proposition number 6.
At prototype or research level, simplicity is the most important asset. Implementing a novel computational method may take weeks in C++, but only hours in MATLAB.
Professor Bohm.
In the latter case, if used properly, computational cost can remain very low.
And the last sentence is the one that interests me. What computational costs are we talking about? Can you give me some idea of computational costs for a given number of degrees of freedom, for a given type of problem, mechanically linear, nonlinear, electrochemical, and maybe also mentioning the hardware you used so I can build a mental picture of what you were doing?
Yes, definitely. So hopefully the opponent, thank you for your question. So here by computational cost, I'm mostly talking about the speed of calculations, either in the assembly stage for adding the effect of individual fibers, or solving not solving many, but mainly the way that we assemble the systems equations, because solver is usually we don't have much interaction with the solver. An example which I can give in this work, which I have really had very good results with MATLAB, is the work which is done in chapter 4, basically, in which we discuss, we have very large number of fibers, huge numbers of fibers. Initially, I started with a C++ implementation of the same problem, and it really could take hours, indeed, because I was using a full system of equation, and it was very demanding the way that the equation was solved. Later on, I devised a different approach. This time I implemented that one in MATLAB, in which I was basically condensing the fiber degrees of freedom, and I was using matrix calculations very effectively to really not to have really to basically reduce the size of the system of equations in a way. And I mean, the 6-7 hours, it really came down to like 20 minutes or so. So it was a very, very huge computational gain in that aspect, which I could really implement it in MATLAB in a way because it offers some vectorized calculations, which are very fast. They are not very memory efficient probably, but in terms of the speed, it's really, really good. And it's really comparable to C++ in many aspects. And it has much less complexity. You can basically implement it in like hours. And if you want to do the same thing in C++, for instance, it would take at least a week, maybe. So also in the implementation aspect, it takes much less.
Okay, thank you. Vale Promovendus, let's go to my second question. You use a considerable number of large arrangements of apparently straight fibers. On page 134, you state that you reach 70 volume% of fibers. Well, from my own experience with building arrangements of short fibers, this is highly impressive. So I would like to ask you a few questions. What method did you use? Do you check your fiber? How do you check your fibers for intersection? Do you have a minimal distance, or are those ideal one-dimensional objects? So how were you really doing those things? And then there's a little bit of the coda, which, however, I think will be covered by another one of the examiners. How realistic are straight fibers?
Okay.
So let's skip the last one.
Okay, I will first discuss the first one, right?
Yeah.
Okay, so it's indeed very challenging to generate this number of fibers with this very high fiber volume fraction. And that's definitely true. But here we are using really the we are adding fibers one by one, and we should in practice assume that the fibers are not interacting in a way. But for this particular example, although we probably could have done it in a very efficient way, it's really possible to do it. But for the generation, we really did not take into account that aspect. So the fibers might be interacting at some point.
Mm-hmm.
So because here the focus was
So they might be intersecting then. Mm-hmm. Okay.
because the focus was basically more on the electrochemical process rather than to be something more realistic, and just wanted to have the same volume fraction as the reference example.
You also have some two-dimensional arrangements of short fibers, which clearly do not intersect. How did you do those? Did you specify some minimal distance between fibers, or what did you actually do?
Yeah, exactly. In the other chapters, we always assume that fibers should not intersect, and for that we check. Basically, we take the fiber diameter as the spacing between the fibers, so that the minimum space between two fibers should not exceed that value, times a certain threshold. I don't exactly.
Which of course has an additional difficulty in there, because if ideal one-dimensional fibers do not intersect, the real fibers might touch, and that might lead to, in the end, to some problems. So one might ask if there was some distance which is larger than the diameter in order to avoid these things, even though this is a can of worms, because it may change the fiber distribution statistics. So did you have a deeper look into that?
No, this was not the focus of our study. We only wanted to just have a certain distribution of fibers, like a random distribution or transversely isotropic. I mean, that was the main focus. Otherwise, we didn't really take into detail.
Did you run any statistical tests on random?
Yeah, we have calculated the tensor in which it is distributed uniformly in all 3 dimensions, so it's isotropic. And if you look at the quantities that we report, they are really show that, like Poisson ratios, they clearly show that the material is isotropic.
Okay, Vale Promovendus, this kind of leads me to my third question. Let me see. In your figure 3.9, that's page 56 in the old version of the manuscript, you do comparisons between effective Young's moduli obtained with your method and analytical methods. You put in Voigt comparisons, but I was a little bit surprised that you didn't do more in terms of bounds, even though you had, because in a way, if you one might play around a little bit more for bounds, but now I think I'm a little bit confused which picture I looked for, because in that picture that I was addressing now, that's exactly what you did. So I must have written up something wrong. So I guess I'll skip that. One more thing with respect to analytical methods. Well, you know, this is kind of my hobby. You went into the Morikawa, which is relatively simple. Did you try some more complex stuff like differential schemes or whatever too? Or is this too far removed from the subject of business?
Yeah, indeed, we did not have, I mean, it was not our objective to really look deeper into the analytical micromechanical models. And we just took some very well-known ones like Hopenside, Morikawa, and just for the purpose of showing how our approach is basically comparable to other basically analytical ones. But no, I mean, we tried numerical because we wanted to basically see the boundaries which are usually not easily seen by the analytical micromechanical models.
Mm-hmm. And to stay with micromechanical methods, Vale Promovendus, I have a final question. In chapter 2, you do 2-dimensional models of line objects, and you repeatedly state that these refer to platelets. Well, if I do a plane stress model of such line objects, they will probably refer to a thin sheet reinforced with fibers. If I do a plane strain, my idea would be that they are ribbon-like objects extending out of the plane of computation. So first question is this really a good model for a platelet? Because I would say it's more for a ribbon. And the other thing is, what I was thinking when I read this chapter, would it be possible to extend your methods in such a way that I have two-dimensional objects of zero thickness, say circles, in a three-dimensional mesh to really do platelets. What do you think? Is that something doable?
About your second question, I don't get what kind of enforcement.
Well, if you take a platelet, I would idealize, let's say you have a circular platelet that's a short cylinder or a spheroid, and if I had to idealize that into a lower dimensional objects, I would get to a circular object of zero thickness. So what you've been doing, you've been using one-dimensional reduced objects. So would it be possible to use two-dimensional reduced objects, circle type, not fiber type, in 3D?
So you mean like a platelet in 3 dimensions?
Yes.
Okay, so first about your first question, it definitely is not the most accurate one for plain strain when we discuss platelets because of the reason that you mentioned. It's definitely not the most accurate one if you want to really model platelets into it. So in that case, we really need to go into the model that we are referring to in the second question, basically, which we have like platelets and which is embedded inside the 3-dimensional material. There are it is definitely from a numerical point of view, it's very easy to do that. It's just, we just need to change a few functions in our code, basically. It's a way that the fiber is actually discretized. Instead of a line element, it should be a surface element. That's from a numerical point of view.
Professor Böhm, are you satisfied with the answer?
Yes.
Thank you very much. And then invite Dr. Gijzelaars to continue the opposition.
Thank you, meneer de rector. Waarde promovendus, ingenieur Boudazi. I read your thesis with great interest and I'd like to congratulate on the completion. It's clear that you've been busy, quite busy the last 4 years, and you even, as a civil engineer, dived into battery chemistry and physics, which I find really impressive. But let me start on my question. And my first question deals with your equation 2.7 on page 17. And there you write down the principle of virtual work, 2 different equations. Yet I see 3 different virtual displacement fields, UM, UD, and UREL. And especially the first of these 2 equations, there is a mix of the delta UM and delta UD. And I was wondering how you solve this. What do I actually get 3 equations, or do you do something that I missed here?
Seriously, the opponent, thank you for your question. So in equation 2.7, we have also UD, which is, we call it basically the duct displacement. It's indeed the displacement of the matrix. It's somehow related to the matrix displacement, so it's not a new field. It's related to the displacement of matrix. So UD is basically a function of UM. So in that sense, we don't have a new field in this. So it's quite straightforward to formulate.
Okay, so UD and UM are actually the same displacement.
They are linked in a way. We define it later on.
Okay, because
If you look at equation 2.15, that's the way that this displacement field is discretized, and it's a function of the matrix displacement in the end.
okay. I was a bit confused about the kinematics. You have the UD plus URL.
Yeah.
You have PEM, and I got the impression that your UD was displacement of the fiber itself?
No, basically here, we define a relative displacement between fiber and matrix, so that is represented by UL.
Okay, thank you. That, yeah, but, in your benchmark problem of section 222, you allow elastic sliding between the fiber and the matrix, but even then you still get quite rich displacements in the neighborhood of the fiber with gradient discontinuity. And then you go into quite some effort to enrich your displacement field of let's say, a lower order finite element system to somehow mimic these richer displacements. And when I look at figure 2.2b on page 15, you show, you sketch the support area of the enrichment as the darker shades and the affected nodes as squared with a square around it. And now I'm wondering what is happening to the elements that are neighboring these affected elements. So the ones that have either 1, 2, or 3 enriched degrees of freedom nodes. Is there anything happening there?
Yeah, definitely. I mean, there is a contribution to the enriched system, which if we integrate this system, there would be contributions at all these degrees of freedom. If you are referring to the numerical consequences of this, we have limited that numerical issues that might happen in the blending region by using big discontinuity enrichment, which is only non-zero basically at the enriched elements. So in the general case, you might have issues with the blending elements, your convergence, lower convergence rate, but here we are using equation 2.27, which is a modified enrichment function which has been tailored for to give the proper convergence rates for the numerical analysis. So we don't have a problem in those elements by violating the partition of unity.
So that means that you're in your equation 2.26, that your function, let's say, call it range y, yeah?
Yes.
That it doesn't extend into the neighboring element.
Yeah, exactly. It's only non-zero within the intersected elements.
But it contains this distance function, zeta, which is a bit of an enigma for me, but maybe can you enlighten me a bit there?
Well, zeta is basically the distance function. So at each point, it measures the distance between that node and the inclusion, the shortest distance. So it can be it's in an absolute form, so it's always positive in
Yeah.
the calculation. And so, I mean, if you basically picture this equation, if you draw it, you will see it's only non-zero at the intersected elements, and it goes away the terms. Because I mean, the original one is the distance function which is used for big discontinuity, and that function has a lot of problems in the blending region. But this function that we are using, and it's detailed in reference 19, it is basically very smart in that sense.
Yeah. Well, I'll have a look at that 19 because my impression of the distance function is that it goes to infinite at infinity. So it gets bigger in the neighboring elements.
Yeah, but we are also subtracting the term from it in the end, so in the end, it's really, well, basically, we only calculated at the region which we have enrichment, obviously. But we are also subtracting that term, so that if you draw it, I mean, it's a bit difficult to just say, we really need to figure it to see, I mean, to see the figure and it's quite understandable.
So out of Promovendus, I'd like to ask another question, if the rector allows it.
There's time for a short question and a short answer.
Well, I wanted to talk to you about the oscillations. You state that these are not of the type discussed in Schellekens and de Bos, but I haven't found an explanation as to what is the actual cause, although you mentioned that there is an hypothesis. Can you first explain me what the Schellekens and de Bos find as an explanation for oscillation?
Well, the ones describing that paper is very different in nature from this one. Here, we only wanted to rule out that one because we also tried a different numerical integration, the Newton codes, because that type of oscillation will be resolved if you use a different numerical integration. And here we have used 4 different sorts of numerical integration for the fibers, for the interface, basically, and we haven't seen any improvement. I can talk about the source of oscillation here.
Yes.
Okay. I think we exactly cannot say there is only one reason, but the most probable reason can be that we don't take into account the weak discontinuities in our embedded models. So because we want to keep it simple and weak discontinuity, the enrichment that we just discussed is very expensive to basically add it in like 3 dimensions or when we have multiple fibers at one element. So most of the embedded models, they just put that one aside.
Dr. Gijzelaars, are you satisfied with the answer?
Yes, thank you, Promovendus, and I'll rest my opposition.
Thank you very much. May I invite Dr. Aragon to continue the opposition?
Dear Director, thank you so much. Father Promovendus, first, let me say that I really enjoyed reading your thesis. I think it's a very solid body of work. You published already your first chapter in CMME, which is a very reputable journal, and what I find also remarkable, as stated before, was the fact that you went all the way not only to develop numerical techniques, but also looking at the physics. So I am having confidence that your last chapter on mechanical coupling to chemistry is going to end up in a really nice journal. So that being said, I have a few questions for you. You know that my line of research is in the field of enrichment element methods, and if you look in page 21, we go back to that equation that you were describing, equation 2.26. This expression is actually remarkably similar to the one that we proposed back in 2012 on the interface on which generalized fine element, right? In fact, this function, if you look at the enrichment function proposed by Nicolas Montt, which is the one that you use here, and you plot that function crossing a quadrangular element, that function is actually non-linear because of the bilinear term. But if you plot that function for a triangular element, the function looks exactly the same as in the one that we use in IGFTM. So the question to you is whether you actually look into the IGFTM at some point and if you manage to try to do something, because I have the feeling that it would work as well as the one that you proposed, with the many advantages that the IGFTM formulation has compared to the generalized fine element version of it.
Zero Korea, the opponent, thank you for your question. Yes, definitely, the approach that you have been working on, the interface generalized finite element, I'm familiar with it, but I haven't really tried it here. I think it can be a really good contribution for the future because, as far as I understood, in that method you can have many lines of discontinuity. Like it's easier, more flexible in handling more very large numbers, and also its three-dimensional extension can come up with a more efficient approach. In this work, we really did not have that the time to really go into look at it much deeper, but definitely that can be a very interesting contribution for the future.
Yeah, we also think so. The fact that your implementation of GFAM using the enrichment function proposed by Moss gives you the most accurate speed profile of all points in the direction that IGFM could also be used for that. Actually, looking at that, what you call the SDERS, or the Strength Continuity Enriched Embedded Enforced model, in your conclusions on page 33, you actually discard this model, right? Because you say that it requires the generation of a background integration mesh and its complexity in a 3D implementation doesn't make the model competitive. That's what you claim in your conclusions. Now, if you think about it, if you really want to resolve properly stresses, you would have to inevitably refine your finite element mesh around your inclusions. So doesn't this have the same level of complexity as just creating an integration mesh and use a more refined model anyways?
Yes, in 3 dimensions here, what I'm referring the complexity for the weak discontinuity is that our problem is a bit different from more standard problems where you have a surface in a 3 dimension. Here we have a line of discontinuity, so you will have 2 perpendicular surfaces at least to be able to resolve this type of discontinuity, and it would require a huge amount of computational cost. Yeah, it's doable for sure, but I mean, at this stage, what I was thinking is we can still make the string field smooth by adding like higher order approach or using a smooth shape function like moving least squares in a way that we basically resolve the smoother string field without being really have to resolve that sharp discontinuity.
But my point is mostly that you basically don't want to do complex computations in 3D and then you don't want to do these intersections, but at the end of the day, you are also using an OP3 implementation to find intersections in the end, right? So why not just doing all of this in the beginning of your simulation, creating an integration mesh and even refine closer to the inclusions, and then you get away with it. You don't have to use an OP3 implementation anymore because you have already your integration mesh that you're going to use for performing the quadrature of your numerical array.
Well, it's correct. We have to, especially in this chapter, we have to really calculate the intersection points. But later on, I came up with a different implementation, which we didn't really have to calculate the intersection points anymore. So the only information in the current implementation that we have is that we need basically is to know which element the fiber node is placed in. And for that, we can use very different efficient approaches to just identify the element in which a fiber node is located in. That's the only information we need as of now with this approach.
Now that you touch this particular point, I am actually very curious about the way you handle those fibers that belong to 2 different elements. Because I just cannot picture the bookkeeping that is required to integrate that fiber where you have basically on one element, you have the shape functions of the original mesh, and on the other element, the other shape function. So you have decoupled these two, but at the same time, the bookkeeping is much harder in implementation.
Its implementation, there is some additional complexity that you mentioned, but I mean, this issue, I mean, it doesn't make inconsistency in the way that we are basically discretizing the fibers in the end. I don't see a major problem. We just may come up with a fiber in which part of it is in one element and some other part of it is in a different element. It's still doable, but yeah, it's probably requires some additional steps in terms of the calculations.
Dr. Aragon, are you satisfied with the answer?
I actually would like to challenge my new director, one of the propositions, if I have the time allowed to do this.
Now, in the interest of time, I suggest we continue with Professor Slang. So thank you very much for your opposition. May I invite Professor Slang to continue?
Dank u wel, meneer de rector. Waarde promovendus. My first question is on figure 1.1 on page 2. This was already indicated by Professor Böhm that I was going to ask this question, because if you look closely to that figure, and then you see that the fibers which are in these composites are actually not straight. And that happens in most of the composites that you make, especially when the fibers are flexible. But still you model them as straight fibers. Is that then correct? Or what is the influence of the curvature of the fibers?
Khalid, the opponent, thank you for your question. Well, yes, as you correctly mentioned, it should, the ideal situation is that fibers are curved in reality. In the thesis, in the result that I presented here, I didn't put anything which we have done with curved fibers. And the reason was to keep it as simple as possible and to just basically discuss the numerical aspect of the work. Addition of curvature is not a major challenge because of the same reason that I just mentioned. We don't have to calculate the intersection points between a fiber and the matrix, so it's very trivial to add any shape, to have any geometry for the fibers, as long as they can be represented by one-dimensional object.
Would that change the mechanism in the material? Would it lead to different stresses? Or?
Yeah, it definitely leads to a different stress field. It has from a mechanical point of view, it has a very important effect. But here I'm mainly talking about the numerical implementation aspects, which are not much changed. It's very slightly changed.
Okay. To continue with that a bit, if you go to figure 2.9 on page 26, there you show actually the actual stress and stiff fields for 3 different fibers. So with different angles, and you see they are pretty random. So, what if I now would like to measure the pull-out stress and stiff of these fibers in an experimental procedure? How should I do that? How should I measure the properties that you need as input for your model?
Well, here, the reason that they are not uniform is, first of all, is because of their orientation, which is random, and also that the fibers are interacting. So this interaction effect is something which is usually missed in many analytical micromechanical models. So here, if you want to do a pull-out test, so you don't have an interaction effect. So you probably take one fiber and take it out, and you define some interfacial traction separation rule to fit the numerics into the experimental results. So I don't see much of difficulty to apply and pull out results to incorporate it basically into our numerical simulation. And we need to find out an interfacial relation which can be easily incorporated into the equations, into constitute the relation of the interface. as an interface rule.
Well, if I do a pull-out of the fiber out of the matrix, then probably the highest stress and stiff is at the middle of the fiber. Where I start to pull, but not at the end. And then your nozzle is actually at the end of the fiber. Correct.
Well, the reason that we have it this way is that, well, first of all, we're not having a pull-out test. So it's a fiber which is, yeah, basically in between, and so we are basically having tension on the specimen. And the other reason is that we are using a very simple interface rule, which is a linear interface. So you can come up with any different shapes from which has been derived from a pull-out test, and then you can use it in the same formulation. There is no, because I mean, if we do a pull-out test with the same embedded model, we get something, as you mentioned, which you have in a pull-out test. So we can't really tune our numerical model with experiments.
Meneer Director, is there time for a small question?
There's time for a small question and small answer.
Proposition number 8.
There we go, Wouter Promovendus. Could you read out loud proposition number 8?
Only the first part.
Only the first.
Okay. In a fair situation, a researcher should be the copyright owner of their published papers.
Professor Slang.
Actually, I don't agree with that because researchers are paid by the university, so I think the university should also have the copyright. And actually, last year, Delft University actually decided to put all published materials that's copyright by publishers to put them online. And they asked me if I agreed with that, and I said, I don't agree only if you take over the copyright, because the publishers will run after you to get some money from you. So if the university takes over the copyright, I said to them, then it's fair to do that. So how do you see that point? Where should be the copyright?
Yeah, definitely. I mean, university should also be partially owner of the copyright, but from my point of view, the content is basically generated by the researcher, although the researcher himself is basically funded by some projects or whatever. So here what I'm pointing is that the publisher should not be the owner in the end. So because in the end, everything is generated by the researchers and is given away for free to the publisher. And the publisher makes money.
Professor Schlammer, are you satisfied with the answer?
Yeah, I'm satisfied.
Thank you very much. May I invite the co-promoter, Professor Simon, to continue the opposition.
Thank you, Mayor Director. Wouter Promovendus. In the thesis, you have developed and implemented several discrete fiber models. In the solid mechanics models, we have only considered axial deformation. And this could be a more divisible approximation in some cases, while in others, the bending contribution should also be considered. And in three-dimensional analysis, maybe the torsional contribution. So you should have maybe the complete kinematics of the fibers available for the model to bulk in a proper manner. Now, do you think that the results that got in the thesis could have been influenced by the simplistic assumption of an axial deformation? I'm referring, for instance, to the fiber neutrality business discussed in section 4.
Yeah.
But it's a statement, it's a general remark.
Hooggeachte promoter, thank you for your question. It's really difficult for me to really say whether the neutrality property will hold. In my opinion, it will hold because with a fully resolved finite element, which is basically the solid finite element, we have also observed. So in that fully resolved finite element, we have all effects of bending, whatever. It's a solid element. So it's not, there is no effect of dimensional reduction in that sense. So, and that was really the purpose, to show it numerically. although I'm not aware of an analytical estimate which really basically also suggests the same fact or not. But that was the whole purpose of doing this numerical analysis using the fully resolved finite element method to basically rule out all of these effects in terms of neutrality.
Okay. Another question, if I may.
There's time for a short question.
Very quick one. You're now working in the Department of Earth Sciences at the University of Utrecht. So you are now, well, you know very well how earthquakes work. Do you think that regional inclusions could be used to mitigate the effect of earthquakes? Suppose, for instance, you have an object you want to protect, like maybe a monument. Would it make sense to plug rigid steel plates in the soil to break highly localized deformation bands?
Well, it's a very, very difficult question. I think very difficult to answer because we are not talking about a small scale. It's a very large scale. The faults are usually like the scale of many kilometers, maybe. And by adding the
Let me interrupt you. Do you remember the results you got in the micro shear band that was completely disrupted by the presence of these tiny inclusions?
yeah.
So, of course, scales are different, but still.
Yeah, that's, I'm just talking about how practical this approach can be. I mean, because we have to put something which is very, very, very large inside Earth, and by doing that, we are adding another line of discontinuity. So it's a very, very, very difficult situation to answer. But I mean, if you assume that we have done that, something like that, it really depends because these rigid ribbons, they are very stiff and they can attract lots of stress. So they can become another source of failure if you're not careful enough.
Professor Simon, are you satisfied with the answer?
The intellectual answer.
Thank you very much. And may I invite the promoter, Professor Sluts, to continue.
Dank u wel, meneer de rector. Waarde promovendus. This is an interesting issue. I've come up with to look at chapter 3. There are many issues regarding it. Chapter 2 with all the oscillation issues, and then the element performance is very, very interesting. What to do, but also chapter 3, if I do a follow-up on the question that your promoter also already started. These stiff line inclusions are nice because they could act as stiffener, but also as they trigger the instability or modify the instability. And you can embed them in a matrix material. In your case, you use a elasto viscoplastic damage model, and that enables you basically to model these shear bands. Therefore, you need a nonlinear model. You need a regularized model as well, because otherwise your shear bands run along mesh lines and are mesh sensitive. And you do that, so this viscoplasticity is there, and there's a relaxation parameter, tau, also mentioned in the thesis. It's on page 47, equation 315. Is at least, yeah, you mentioned there in the equation the parameter, and you choose it as a fixed value, right? And my question is, this relaxation parameter sets the shear band thickness to some extent, because also the rigid line inclusion basically let the shear band start from a zero width and then it extends to a certain size, and that size is to a large extent set by this relaxation parameter. And my question is, because this precursor is there, and the length scale that you have should be larger than the line inclusion size, but also larger than the element size.
Polarized.
Thank you, Madam Beaton. May I request the promovendus and his audience to follow the beetle and leave the room, perhaps maybe picking along maybe you could close the